Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about Coulomb's law, and I'm kind of going to be introducing the concepts of charge and electrostatic forces. So let's get into all that. This lecture is kind of the introduction to a bunch of things. So there are some new concepts here that we haven't really seen in Physics 1, but we're really still building on Physics 1 concepts, just with some additional layers in some sense. The first new thing is charge. We represent charge with the letter Q, or sometimes with a capital Q. Basically, I use a lowercase q to represent a point charge, and an uppercase Q usually to mean like an object that has a total charge on it. And the unit is the Coulomb. And so that is spelled like this, and the unit is 1 Coulomb. In some sense, this is a base unit in physics. Technically, the correct base unit is the ampere. The ampere represents a Coulomb per second. That doesn't really tell us much, but that is what this part is. Charges basically is a conserved quantity in nature. There are charged particles or charge carriers that exist in nature. Some of the ones that you're probably most familiar with or have heard about are the electron, the proton, maybe an alpha particle, and antimatter particles, so like antiproton, positron, etc. And then virtual one, basically an electron hole. This is a virtual particle. The charge that we use for these is in units of what's called the elementary charge. So this one would be -1 of the elementary charge. This one is +1 of the elementary charge. This one is actually +2 of the elementary charge. This one is -1 of the elementary charge. This one is +1 of the elementary charge. And this one is +1 of the elementary charge. What are these things anyway? So charges have positive or negative signs to them. This elementary charge, 1e, is approximately 1.602, so less than 1.602, times 10 to the minus 19 coulombs. Okay. So again, I haven't really answered the question, what is a charge? And that is by design. There's kind of a bit of a philosophical underpinning to all this. Stanley Yaki, the great philosopher of science, sort of relates a story, I guess, in one or another of his collection of essays about James Clerk Maxwell, who himself was one of the greatest physicists of history, and greatest mathematicians as well. James Clerk Maxwell, at some point in his career, went on a tour of one of the newfangled, if you will, electrical plants in, I guess, Scotland is where he was from, so presumably Scotland. And the engineer that was giving the tour was explaining how everything worked, and he kind of towards the end of the tour asked, are there any questions? And Maxwell asked him, what is a charge? And the engineer was completely flustered. He didn't know how to answer it. And Maxwell, after allowing a little time for this guy to be flustered, said, I ask this because it's the only question to which neither you nor I know the answer. So what is a charge? It's kind of hard to define what it is, but I can tell you a little bit about what it does, what its effects are, that kind of thing. So charges are the things that have to move in order for there to be current present, and that is how we define the units of current, amps. Their amount of charge moving per unit time. Although there is a second definition, which I'm not going to get into today, that has to do with how much force per unit wire, per unit length does a pair of parallel wires placed some distance apart apply to each other while the current is flowing through them. These charged particles also have mass. For example, the electron has a mass, m sub e, of approximately 9.11 times 10 to the minus 31 kilograms. The proton, mass of a proton, this one is more like 1.6 something, is 1.67 times 10 to the minus 27 kilograms. There's also, I didn't list it over here in the list, there's the neutron. 0 charge. But it has a mass of approximately 1.67 times 10 to the minus 27. It's actually slightly more massive than the mass of a proton. So the mass of the neutron is very slightly larger than that of the proton. In fact, it's very slightly larger than the proton plus the electron. The alpha particle has 2 protons and 2 neutrons present, and so it's basically a helium nucleus. Antiproton has mass of a proton. Positron has mass of an electron. Electron holds a virtual particle. It doesn't actually have mass. It basically is the equivalent to taking an atom and removing 1 electron from the outer orbit of that atom. It's a useful concept for doing charge carriers, for doing current, that kind of thing, but it's a virtual particle only. So what is another effect with charged particles? Well, they apply forces to each other. So charged particles apply forces to other charged particles. They also produce what are called electric and magnetic fields. They produce electric fields just by being charged. They produce magnetic fields by being charges in motion. But those are both topics for another day. What does the force of 2 charged particles look like? Well, let's say that I have a charge here. We'll call this charge Q1. And let's say that I place another charge somewhere over here. We'll call this one charge Q2. The force between these two is going to be given by some combination of how much charge is present here, how much charge is present here, and how far apart they are. This distance between the two of them, even though it's a distance and therefore we might say is a d, is conventionally represented by the letter r. I think that convention probably comes from the fact that one of the standard models for, or one of the early-ish models for a hydrogen atom, or for atoms in general, was to have the proton here in the nucleus and the electron orbiting in basically a circular orbit about that proton. And so the radius of that orbit, r, is also the distance between the proton and the electron. I think the Bohr model of the atom expanded on this and gave an approximate radius of about 5.2. This is called Bohr radius. It's about 5.29 times 10 to the minus 11 meters for hydrogen atom. But in any case, we'll just denote this distance as r, not d. So essentially, what is found is that force is proportional. This symbol right here means proportional to, and actually, instead of using this symbol, I'm going to use a single tilde to mean force will increase linearly as variable afterwards increases by whatever factor is shown. So F increases linearly with the amount of charge. And that ends up being true of this charge. It ends up being true of that charge. It also ends up increasing, really decreasing as the distance between the two charges increases. So Coulomb's law basically takes all of these things and puts them together. Coulomb's law says that the force between these two charges should be proportional to the product of the charges divided by the distance squared between the charges. And the proportionality constant is what's called Coulomb's constant. Okay, so here's your Coulomb's law. K sub c is what's called Coulomb's constant. And what you end up getting for K sub c is approximately, I'll go out to 3 sig figs, 8.99. You could think of this as approximately 9.0, but we'll say 8.99 at 3 sig figs times 10 to the 9. And the units that go with it are Newton meters squared per Coulomb squared. So you need to know that fundamental constant. Okay, so that's Coulomb's law. The Colorado PhET simulation allows you to basically simulate Coulomb's law. And if you're watching this video just because you found my channel, or because you're taking one of my classes in person and you're not really doing virtual labs, that's fine. And hopefully you're finding this helpful. But if you are taking a course from me online and I'm doing virtual labs, then you'll actually use the PhET simulation to probe Coulomb's law. For the rest of you, you can go dig up the Colorado PhET simulation. Just type in PHET and look for the Coulomb's law simulation. It allows you to test out this law if you'd so desire. But this law is the fundamental law for governing electrostatic attraction. For what it's worth, we could compare the Coulombic force between two charged particles, which looks like K Q1 Q2 over R squared, versus Newton's fundamental law for, Newton's universal law for gravitation, which looks like negative G times M1 times M2 divided by R squared. So these two laws are like each other in that they both have a fundamental constant times a product of relevant terms divided by the square of the distance between the two objects. So they're like in that manner. They are different in that whereas the Coulomb's constant is large, the universal gravitational constant in Newton's law is actually very small. You can see there are roughly 20 orders of magnitude between just those two constants. Furthermore, charges tend to be kind of larger magnitude than masses for charged particles. So comparison, if you're looking at 2 protons in each case, then you have here about 8 orders of magnitude per term here for these versus these. So you get a lot more electrostatic force. However, you do have negatives as opposed to negatives and positives, so you can cancel out Coulombic force but not gravity. One last thing to note about charges here and Coulomb's law is that with Coulomb's law, like charges attract each other, repel each other, and like charges attract each other. And so Coulomb's law could have an attractive, or we might say negative force, where they're pulling each other towards each other. It could also have a repulsive, or what we might call like positive force, whereas gravity, it's always attractive or negative. Among other things, this means that charges can shield each other. So if I have like a plus charge and then a minus charge and another plus charge, they can be placed in such a way that each of the three experiences zero total force. You can't really do that with gravity. We don't have a way to shield this gravity from, or this mass gravity from this mass gravity by putting more mass over here. You can get it to where you have a mass here and like maybe two here and here, such that this one has zero total force, but these two will still be pulled towards it. What this means is that on the macroscopic scale, gravity tends to dominate, because as you add more gravity to a system, you're always adding more force. Whereas charges, you can be adding a plus and a minus and a plus and a minus and a plus and a minus and have a total net charge of zero or something really small. So let's do a quick example of Coulomb's law to round out this video. All right, so I've got a pair of charged objects that we're going to treat as point objects. They're 3 meters apart. Each one has a charge of 6 millicoulombs. Diagram of this situation: here is 6 millicoulombs. Here is the other 6 millicoulombs. This distance right here is 3.0 meters. Note that 1 millicoulomb is the same as 10 to the minus 3 coulombs. So these are both 0.006 coulombs. So with that little preamble aside, the force between these charges should be, according to Coulomb's law, K Q1 Q2 over R squared. That is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared, times, if we do this in scientific notation, these are both 6.0 times 10 to the minus 3 coulombs. And then the distance separating them is 3.0 meters quantity squared. You should be able to put all those numbers into your calculators to get a result. Excuse me, the result should be about, I haven't put it in yet, but I think it should be about 3.596 or something like that times 10 to the 4. So let's go ahead and put that in. So 8.99 times 6 times another 6 divided by 3 squared, which is 9, and then that's times 10 to the 9 minus 3 minus 3, so 10 to the 3. So that comes out to 3.596. 3.596 times 10 to the 4. And the unit, of course, is for force is newtons. And note that I only had to solve this one time. The first charge and the second charge apply equal amounts of force to each other. If we were to change the problem so that one of them is, let's say, 6 and the other one is 65 millicoulombs, the amount of force being applied would be different, but each charge would still apply the same amount of force to the other charge. You can do that by plugging those numbers into Coulomb's law for each one, or you could just simply use Newton's third law from Physics 1. This force is a repulsive, so if I was going to draw a free body diagram here, showing the direction of these forces. This one would have a force this way. This one would have a force this way. We could call this force 1 acting on 2. This would be force, this would be force 2 acting on 1. And then the other one would be the force of 1 acting on 2. If we replace one of these with a negative charge instead, so let me draw a little diagram. What if one of them happened to be negative and the other one happened to be positive? Then our force diagram would look like this. So again, this is force of 1 on 2. This is force of 2 on 1. And these charges, this one is Q1, this one is Q2. Q1 and Q2. All right, this video has now run a bit over the 15 or even 20-minute mark, but only just. That's because it being an introductory video, there was quite a lot to have to say. Hopefully you found the time to be well spent, and I hope you've learned something from watching all this. So thank you and enjoy.